In this lecture, we are going to see how the matrix displacement method can be used to analyze indeterminate trusses. We start by writing the relationship between member-end forces and displacements in matrix form. Consider a truss member with a length L. Let's label its ends I and J and label the angle that the member makes with the x-axis theta. Since the member is part of a larger structure and that structure is being displaced, we can assume that joints I and J are undergoing displacement as well. I am going to show the displacement at each joint in terms of its x and y components, like this. The truss member has 4 degrees of freedom, 2 displacements in the x direction and 2 displacements in the y direction. We can also define 4 member-end forces, like this. There are 2 forces in the x direction and 2 forces in the y direction. As was explained in the previous lecture, the relationship between the displacement vector and the force vector can be written in matrix form, like this. This is called the member stiffness matrix. Before I explain how these coefficients are calculated, let me show you the results. For a member with a length L, a cross-sectional area A, and a modulus of elasticity E, the stiffness matrix becomes where C represents cosine theta and S is sine theta. But how do we come up with these coefficients? To answer this question, let's start by changing the coordinate system. I am going to define a local x-axis along the length of the member, like this. For convenience, let me rotate the member clockwise so that the x-axis becomes horizontal. We refer to this as the member or local coordinate system, whereas this is called the system or global coordinate system. In the local coordinate system, our truss member has only 2 degrees of freedom, the axial displacement at ends I and J. Let's label them U1 and U2. We can then define a force at each end of the member. Let's label them P1 and P2. Like before, the relationship between displacement, U, and force, P, can be expressed in matrix form. From the previous lecture, we can recall that W11 is the stiffness coefficient for the force displacement pair P1U1. This means if the bar is displaced axially by distance U1 while U2 is 0, an axial force of P1 results. This force equals to U1 times W11. We can also relate the axial force to the axial displacement using this equation. Where sigma is axial stress, E is the modulus of elasticity of the material, and epsilon is axial strain. Knowing that axial stress is force over cross-sectional area, and axial strain is displacement over length, we can conclude that W11 equals EA divided by L. The other coefficients of the stiffness matrix can be computed in a similar manner. Here is how we can determine W12. The coefficient is for pair P1U2. That is, if we give the truss member an axial displacement of U2, then the force caused at the left end of the member, which we refer to as P1, is W12 times U2. Using the axial stress-strain relationship, we can write, or, since the force equilibrium must be maintained in the member, P1 equals negative P2, or, comparing these two expressions, we can see that W12 equals negative EA over L. We can determine W21 and W22 in the same manner. Thus, the member stiffness matrix in the local coordinate system can be written as Before we can use these equations to model an entire truss, we need to transform the coordinate system from the local to the global system. When transformed, as I mentioned before, we get this system of equations. But how exactly does the local system transform into the global system? Let's take a look. In the local coordinate system, we labeled the displacement at this end as u2. In the global coordinate system, the same end displacement is labeled d3 and d4. This means the projection of d3 onto this axis plus the projection of d4 onto the same axis adds up to u2. So we can say, similarly, for u1 we can say, expressing these two equations in matrix form, we get We label this matrix T and call it the displacement transformation matrix. We can also come up with a force transformation matrix. Here is the member end force in the local coordinate system, and here are the member end forces in the global coordinate system. What is the relationship between these forces? Since this is an axially loaded member, we know F3 and F4 must be the components of P2. Therefore, similar equations can be written for the other end of the member. That is, in matrix form, these equations become Let's label this matrix Q and call it the force transformation matrix. Now we are ready to show how to transform the member equations from the local coordinate system to the global coordinate system. We begin with multiply both sides of the equation by matrix Q, the force transformation matrix. Given equation 2, we can replace the left-hand side of our equation and obtain Substituting the right-hand side of this equation with equation 1, we get Now, all that remains to be done is to determine the product of these three matrices. If we let C represent cosine theta and S be sine theta, the matrix product can be written as This is the member stiffness matrix in the global coordinate system. Let's put this to use and analyze a simple indeterminate truss. Consider this 3-bar truss. The structure has only 2 degrees of freedom. We can label them D1 and D2. Therefore, for the entire structure we can write This is the system stiffness matrix, and this is the vector of the joint loads, which equals We determine the stiffness matrix coefficients by using member stiffness matrices. First, we need to write the stiffness matrix for each member. As a reminder, here is the generic matrix. For member AD, the length is 5 meters, and the inclination angle, theta, is 53.13 degrees. Therefore, we get For BD, L is 5 meters, and the inclination angle is 180 minus 53.13, or 126.87 degrees. That gives us For CD, the member length is 7.21 meters and the inclination angle is 146.31 degrees. We are now ready to determine the coefficients of the system stiffness matrix. Please review Lecture SA47 if you are not sure how this is done. K11 of the system matches K33 of AD, K33 of BD, and K33 of CD. Thus, substituting in the member stiffness matrices, K11 becomes K12 of the system matches K34 of AD, K34 of BD, and K34 of CD. Therefore, since the stiffness matrix is symmetrical, K21 equals K12. K22 of the system matches K44 of AD, K44 of BD, and K44 of CD. Thus, so here is the system of equations that we need to solve. Use your method of choice to solve the equations for the unknown joint displacements. D1 and D2 are Now that we know the joint displacements, we can use the member equations to calculate member end forces. For member AD, we have or for BD, we get for CD, we have Here are the member end forces shown diagrammatically. Here are the results of the analysis, the member forces and support reactions. We are going to illustrate the use of this method for truss analysis further in future lectures.